Chapter 5 takes a different direction, discrete probability distribution. So we talk about a probability distribution here. Random variable x is a numerical measure of the outcome of a probability experiment. So its value is determined by chance. Now, we have two types of random variables. We have what's known as a discrete random variable that would be either finite or countable, meaning you could count how many of those there are, such as how many integers are between 0 and 4 inclusive. Well, there's 1, 2, 3, 4, 5 of them. Versus a continuous random variable has infinitely many values. Tell me all the real numbers between 0 and 4 inclusive, including those. There's no way of listing all of them. 0, 0.1, 0.01, 0.001. Heck, I can never ever get to 2 if I want to list all of them. Now, we're going to really set up a couple of examples to clarify this and go from there. Identify the random variable and the sample space. If I toss a coin and I'm looking for heads, we let x be the number of times a coin lands on heads. The sample space, I flip a coin, I toss a coin once. X could be either 0, 0 means no heads, or 1 head. That's it. On a number line, that would really be either a 0 or a 1, one of the two. That's the entire sample space. Versus an experiment that measures the time between arrival cars in a drive-thru. Let t be the times, you could call it x as well, times between car arrival. Between car arrivals. The sample space, t is bigger than 0. That's all we know. And the reason for that, well, cars are not going to arrive in negative time. They're going to arrive by waiting some time after the other. And 0 not included. And here, unlike those two options, I'm really going to shade all of that because a car could come, or the waiting time or the arrival time between two cars could be a second, 2 seconds, 3 seconds, 10 seconds, a minute, 2 minutes, an hour, 2 hours, 1.5 hours, 1.7 hours. So the options are limitless. That makes it continuous. Of course, continuous is more challenging to predict than countable. We're going to focus on countable in those sections, chapter 5 basically. So, in chapter 6 and on, we take on the continuous. Probability distribution. A probability distribution is a description that gives the probability for each value of the random variable. It is often expressed in the form of a graph, table, or formula. Now, this is what's so special about a probability distribution. If you add up all the probabilities, you should get 1. 1 means 100%, where x assumes all the possible values. And 2, each probability must be between 0, that's 0%, and 100%. It can be bigger than 100% and it can be negative for each individual event x. So I'm looking at the first example, and the first example is saying, well, are the following a probability distribution? If not, state why. We glance for the obvious. Are any of these probabilities bigger than 1 or negative? No. Well, what's the next thing to do? That's satisfied. I need to add them up. I need to add up all of these probabilities and see if they add up to 1. If I add them up, and here's my calculator, should have had that prepped. And you really want to get into the habit of using your calculator constantly. Here we go. So here's the calculator. If I take 0.16 plus 0.18 plus 0.22 plus 0.10 plus 0.30 plus 0.01, 0.97. So the answer is no, it is not. Why not? Because it doesn't add up to 1. How about the second example? Example B. Well, there's a negative probability. Automatically we say no. And why is that? Well, it's obvious. We have one negative probability. And how about the third case? Well, all of these are fine. And I noticed that they're the same as those. The only difference, instead of this being 0.01, this is 0.04. So if I take the sum of p of x, since I already have my calculator, all what I have to do is go back and change that to a 4. And that gives me a 1. So this one, yes, each probability is between 0 and 1, and the sum is 1. Very good. Now, we're going to show you how complex things could get. We want to create a probability distribution. A couple planned to have 4 children. Let x be the number of boys. So when you say x equals 0, you're saying no boys. Here you're saying 1 boy. Here you're saying 2 boys. Here you're saying 3 boys. And here you're saying all 4 children happen to be boys. The couple will have, find the probability distribution. So this is only with 4 children. Imagine if a couple have 10 children. Well, this is a bit more complex than you think, and this is how it works. You would start a tree. You know what? I will use this skinnier. Here we go. A tree diagram will be very useful. So the choices for the first child, they either get a boy or they get a girl. For the second child, a boy or a girl. Now, isn't that always the option, regardless of whether they get a boy first or a girl? Then for the third child, it's going to be a boy or a girl, regardless of what they got the first 2 times. Now I'm going to see if I could expand this a bit. I can go this far. And then for the fourth child, as you see, it's getting very rough. The way it works, if I want to list those, I would list, the only way to reach there is to go boy, 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 but that means this is them having all boys, right? To look at this, that's 3 boys and a girl. Then it's a boy, boy, girl, boy. Boy, boy, girl, girl. And if I go in the list, boy, girl, boy, 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 girl, boy, girl. Then boy, girl, girl, boy, boy, and 3 girls, right? That's all the way down here. Then I could start with the next girl, boy, 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 girl, boy, boy, girl. So I'm just reading each of those from left to right, right? Girl, boy, girl, boy, girl, boy, girl, girl. 2 girls in a row, a boy and a boy. 4 girls, girl, girl, boy, girl. and girl, 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 and a boy. So for example, if I'm looking at this, that is 2 girls, a boy, and a girl. That path. So if I look at those, I want to know what's the probability of each of those, and this is how I do it. No boys. That means only girls. There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 16 possible choices, and only one of them satisfies that event. As for only one boy, well, that's 4 boys, that's 3 boys, that's 3 boys. You're eyeballing where is there only one boy. I see one right there. I see one right there. I see one right there. That's 1, 2, 3. And I missed one. Oh, that would be this one. So that is 4 out of 16. Now, as you go inner more, that's a bit more difficult to find. So instead what we do, we find the easier. How about 4 boys? Well, there's only one way of getting 4 boys. And how about 3 boys? For 3 boys, 1, 2, 3, 4. Well, guess what? I'm going to use the fact that this is a probability distribution. If this is 1 over 16, and this is 4 over 16, that's 5 over 16. That's 10 over 16. To add up to 1, if you have 10 over 16 and you want 16 over 16, what do you do to the top? That must be a 6 out of 16. And if you add all of those, you get a 1. So if you add up all of these probabilities, you will get a 1. Of course, in decimal, that's a bit messier. And this is 0.25. This is 0.375. This is 0.25. And this is 0.0625. So this is only if you're choosing 4 children. Imagine if you have not children, you're talking about employees, and you have 50 employees or 70 employees. So the work could be tremendous. Now, okay. The average is the sum of x times its probability. This is the letter mu, that's for our mean. The variance, well, we don't use the variance much. We really use the variance for the standard deviation, is the square root of x squared times p of x minus the average squared. We really don't use this. We use this more. Round off, we always carry one more decimal place than what the random variable brings in. And here's a problem. In a study of brand recognition, random groups of 4 people are interviewed. Let X be the number of people who recognized Jeff Bezos when shown a picture. So 0 means none of the 4 were able to recognize him. Only 1, only 2 recognize him, only 3, all 4 recognize him. The following probability distributions are given. Well, if I want to find the average given X and its probability, first I add up the probabilities, and if I add those, I must get a 1. Then I multiply those two, 0 times 0.01, 1 times 0.10, 2 times 0.24, 3 times 0.30, and 4 times 0.35, and I add them up. So if I take, let me put that in, here we go. So if I take, the first one is a 0, of course. 1 times 0.10 is 0.10, plus 2 times 0.25, plus 3 times 0.30 or 0.3, plus 4 times, oops, 0.35. I'm getting 2.9. I think I messed up. 0.10 plus 2 times 0.25 plus 3 times 0.30 plus 4 times 0.35. I found a mistake. That's a 24, not 25. So if I go to my calculator and I go back twice, enter, and if I go back and make that a 4, there it is, 2.88. Now here I'm going to take x squared, 0 squared times 0.01, 1 squared times 0.10, 2 squared times 0.24, 3 squared times 0.30, and 4 squared times 0.35. That's how I find the average and standard deviation. So if I go in now, I have two options. I could go back and put a square for each of those, or I could redo the whole thing from scratch. So here, I'm going to insert, I'm going to make that, well, 2 squared is a 4, 3 squared is a 9, and 4 squared is 16. I'm going to insert a 6, and I'm looking at what I get, and that's 9.36. And now if they say, what is the probability that more than 2 people, probability that more than 2 people, according to the table, isn't that 3 or 4? Will recognize Jeff Bezos? Well, what do we have? We have 30 plus 35, so there's a 65% chance that more than 2 people will recognize Jeff Bezos. What is the probability that at most 3, at most 3, so no more than 3? This is how we're going to do this. This is something we're going to use a lot. The choices of x are 0, 1, 2, 3, or 4. And we're going to use the complement always. Isn't that this condition? That is 1 minus the probability. What is left? What did I leave out? Do you see I only left out 1? So that's the complement. That's 1 minus. What's the probability that all 4 recognize them? Isn't that 0.35? That's going to save us a lot of work. So there's a 65% chance of that happening. Find the mean. Find the mean number of people who recognize Jeff Bezos. Well, the mean is the sum of x times p of x. We got it to be 2.88 since they're given us. So it's roughly 2.9 since they're giving us 1 decimal. And find the standard deviation. Well, standard deviation is nothing more than the square root of the sum of x squared p of x minus the mean squared based on what we have. We summed those up. We got 9.36 minus 2.88 squared. And if I plug this in my calculator, if I could do it forward, that is, take the square root and make sure to use parentheses, 9.36 minus 2.88 squared, and I'll get that to be 1.032. Now we're going to use this for something else. Okay, well, we already know that the expected value denoted by E of a discrete random variable, that's what we call the average. Expected value is what you would expect, which is about the average. That's what we expect normally. So here's a game. There is a game in Vegas where you pay $1 to play. So you're going to put in $1 to play with a possibility of winning either a 5 or a 10. the probability of a payout of 4. So you win $5. Remember, if you put in $1, so you could lose that dollar. You could win $5. If you really won $5, doesn't that mean you really won $4? Because you gave them $1, they gave you 5. And if you won $10, doesn't that really mean that you won $9? So I play this game, I give them $1. There's a chance that I won't win. That means I lost $1. There's a chance I'll win $5, but I gave them $1, they gave me 5. I really won 4. And there's a chance you could win $10. I gave them $1, they gave me 10. I really won $9. So this is the net. Now, the probability of winning $4 is 30%. The probability of winning $9 is 10%. Find the expected value. Well, we know that those probabilities must add up to 1. What must this be? If this is 30% and this is 10%, those are 40%. I could use my calculator, or I could say, well, there's a 60% chance that I might not win anything. If I play this game, I should expect the sum of x times p of x, that is -1 times 0.6 plus 4 times 0.3 plus 9 times 0.1 or 0.10, it's the same thing, 1.5. That is a positive $1.5. Now, what does this mean? This means if I am to play this game long enough, I would expect to win $1.50 per game if I play this game long enough. Remember, the only way these numbers are attained if n is extremely large. Interpretation of the average over a long time. That is, if we play this game many times, we expect a profit of $1.50, which means this is a game you should play. By the way, there are no games in Vegas in which the expected value is positive on your end. It's always positive on their end, otherwise they wouldn't have it. Here's another problem. If I look at insurance policies, when someone buys a life insurance, that policy pays out a sum of money to a beneficiary upon the death of the policyholder. Suppose a 25-year-old male buys a $150,000 one-year life insurance policy for $250. The probability that the male will not survive is this much. Now, the experiment has two outcomes. Either the person is going to survive or the person is going to die. Let x be the random variable that represents the money lost or gained by the life insurance. Well, the life insurance could win $250 if the person survives, right? Or they could lose, it's not $150,000, they already collected $250. So they could lose, they gained $250, but they could pay $150,000. What would that be? If I take 250 minus 150, they could lose 149,750. I don't like that. One key. We said they could lose $149,750. Well, they would lose that if the person dies. The probability of dying is 0.0013. What's the probability of not dying? 1 minus that. 1 minus 0.0013. there's a 99.87% chance that a person will survive. From the insurance point of view, the average or the expected value is going to be the sum of x times p of x. And what is that? That is 250 times 0.9987 plus a negative 149,750 times 0.0013. If this number is positive, then the insurance will make money on the long run. They just have to sell enough policies. And if that's negative, they're going to lose money. So if I take 250 times 0.9987 minus $149,750 times 0.0013, that turns out to be positive 55. That's the answer to the problem. What does that mean? That means the company should expect to make $55 per policy if they sell enough policies. Over 1,000 policy, how much should they make? Well, 1,000 policies, expecting to make, so 1,000 policy times $55 for each one policy, we should expect them to make $55,000. And that's why insurance companies try to get as many people as possible.